So in the last video, we learned about these ortho para-directing groups versus these meta-directing groups. And we know, for example, if we have a benzene compound with this electron donating functional group, some kind of functional group that donates electron density, we know that's going to favor adding this bromine compound on the ortho position, creating this product, or in the para position, creating this product. And we explained why that is, and we explained that in the last video. I have a link of it below. I recommend you watch that before you watch this video. But the point is, if we have an electron donating group, we're going to favor adding the bromine on the ortho and para position. So we're going to have a mixture of these two products. However, if we have an electron withdrawing group, which withdraws negative electron density, then it's going to favor adding this bromine on the meta position. It's going to favor adding the bromine on the meta position, creating this product. And again, we explained why that is in the last video. So there are these two categories. There are ortho para-directing groups, which are electron donating, and there are meta-directing groups, with their electron withdrawing. There are these two categories you should be familiar with. So now let's do some examples. Let's say we're taking an exam. And we have this problem. And we're asked, is this in an ortho para-directing group? Or is this a meta-directing group? Which category? We have these two categories. So is this ortho para-directing or meta-directing? So how do we solve this? Well, the way I like to do this is the first thing I do. The first step is I imagine adding the bromine on the ortho position. That's always the first step. The first thing I'm taking an exam and I simply just add it on the ortho position and I see what happens. So when we add it on the ortho position, we create this intermediate, this transition state. And we know whenever we add this bromine and we add it, we're going to be stuck with the positive charge. But if we add it on the ortho position, we create this transition state. And we think, is this stable? Is this transition state stable? Well, let's think about it. We have a positive charge here because, again, we know when we attack, we form that bond. So we form this bond. But then this carbon loses its electrons. It lost electrons in this pi bond, so now it's positively charged. However, it's right next to this electron donating functional group. We have resonance. Essentially, these lone pairs of electrons can fall down, forming a double bond, having resonance, delocalizing that positive charge. Delocalizing that positive charge over a larger region, which is stable. So essentially, that resonance is stabilizing this positive charge. So this makes sense. This is reasonable. It makes sense to add this bromine on the ortho position, because we create this stable transition state, which this positive charge that's stabilized with this resonance. So this makes sense. And then we know the next step is we have a hydrogen that we deprotonate and the electrons would fall back down, creating our final product. So therefore, we know adding it in the ortho position makes sense. That makes sense. So therefore, we know this is in the ortho para category. So this compound is electron donating and it's in the ortho para-directing group category. So that's the answer. It's ortho para-directing. And we know whenever we have an ortho directing group, that's if it's stable adding it ortho, that also means it's stable adding it para. And again, we explained why that is in the last video. But now we know this compound is ortho para-directing group. So now let's do another example. Let's say we have this compound and we want to find out, is this an ortho para-directing group or is this a meta-directing group? And again, remember, the first thing I do, if I'm taking an exam and I have this problem, the first thing I do is I imagine adding this bromine on the ortho position. That's always the first thing I do. I just add it on the ortho position and see what happens. So when we do that, we have this product, where again, these electrons essentially attack, forming that bond that's represented by this bond, and then this carbon loses its electrons, forming this positive charge. So we add it on the ortho position and see, is that reasonable? Does this make sense? Well, no, this is not stable. Because again, we know this nitrogen, we can see based on how many bonds it has a formal charge of +1. This is a positively charged nitrogen. So this nitrogen is positively charged. So does it make sense adding this bromine on the ortho position, creating another positive charge right next to this positively charged nitrogen? No, having these two positive charges next to each other is not stable. This is not stable. So therefore, adding this bromine on the ortho position is not stable. That's not reasonable. So therefore, it doesn't make sense to add it in the ortho position. And we know these are in the same category, so therefore it's not stable adding it in the para position. So this is not stable. So therefore, we know it must be a meta-directing group. If it's not stable adding it in the ortho para position, then we know it must be a meta-directing group. So therefore, we know this is a meta-directing group. And it's an electron withdrawing group. And this is not stable. So that's how I solve these problems. if I add it on the ortho position, and if I add it on the ortho position and that makes it and it's stable, then we know it's in the ortho paradirecting group. However, in this example, again, the first thing I do is I add it on the ortho position. And if that's not stable, again, in this example, we add it on the ortho position. If that's not stable and that doesn't make a stable transition state that's not stable, this intermediate that's not stable, then you know adding it on the ortho position is not right. So therefore, we know it's in this category. It's in the meta-directing group category. So that's how I like to solve these problems. And so let's do another example. And then again, so therefore we know this one again was meta-directing. So let's do one last example. Let's say we have this compound. So again, is this going to be in the ortho paradirecting group category or in the meta-directing group category? Well, again, remember, first step is I just imagine adding it on the ortho position. These electrons attacking, adding it on the ortho position. That's always the first thing I do. So we add it on the ortho position. And what happens? We create this intermediate. Let's think about it. Is this transition state intermediate stable? Well, notice we have resonance. Again, we have resonance. These electrons can fall down, forming that double bond, and when we do that, we delocalize that positive charge. And we even have more resonance. So we can really delocalize that positive charge. So we have this electron donating group that can stabilize this positive charge. So therefore, adding this bromine on the ortho position is stable. This is stable. So therefore, we know adding it on the ortho position is reasonable. So therefore, we know this is an ortho paradirecting group. Because again, if it's stable adding it in ortho, it's also stable adding it paras. And we explained that in the last video. So therefore, this is in the ortho paradirecting group. And therefore, it's not meta-directing. And that's how I like to solve these problems. And then again, this hydrogen would get deprotonated, again, with it forming our final product. And again, that's how I like to solve these problems. We have those two categories, ortho paradirecting or meta-directing. And the first thing I do is I simply just add it in the ortho position. I add it in the ortho position, and if it's stabilized, that transition state stabilized, then you know it's ortho paradirecting. However, if you add in the ortho position and it's not stable, that's not stable with these two positive charges nearby, and it's not stable, then you know it's not ortho paradirecting and it must be meta-directing. So that's how I solve these problems. So let's do this one last example. So we know this is electron donating. This compound is electron donating. It donates an electron density, so it's electron donating. So we know when we have electron donating group, it favors adding these compounds on the ortho and para position. And again, this is another ortho position. So that's what electron donating groups likes to do. But we don't just have this electron donating group, we also have this electron withdrawing group. This is electron withdrawing group. And again, in the last video, we explained why this is electron withdrawing. It has that positive charge, so it withdraws electron density. And we know when we have electron withdrawing groups, this would favor adding it on its meta position. So we know this guy relative to this guy, the meta positions would be here and here. So again, this guy favors ortho and para, and this guy's ortho and para groups would be these carbons. And we know this guy likes to add it on its meta positions, its relative meta positions. And we know its meta positions are these two carbons, So therefore, where will this bromine be added? Well, we see this guy wants to add it in these carbons, while this guy wants to add it on these carbons. So they're working together. And so therefore, these two carbons are very favorable. It's very favorable to add this bromine on these two positions. So therefore, these are the products will be made. What this position is very favorable. We know this position is very favorable. Adding it here, that's very favorable. So we'll add it here, forming this product. And we know this position is very favorable. So we can also add it here, forming this product. So in this example, they're working together. They're teaming up. They both want it to be added on these positions. So there's a strong driving force to add it on these two positions because they're working together. And again, the point is, this is essentially electron donating, so it favors a position, and this is electron withdrawing, so it favors a position. But in this example, they're working together, so therefore it's going to add on these positions.